All right. So, on Friday and Saturday, we looked at, or sorry, Thursday and Saturday, we're in class. We looked at how the, how the graphs of the sine and cosine work, okay? And so we kind of learned all the bits and pieces of that. What we're going to look at today are how the graphs of the other four trigonometric functions work, okay? So today we're looking at graphs of all trig functions. Okay? So, to start with, what I want to do real quick is just go over, again, the parts of the sine graph, okay? And actually throw a sine graph up here, okay? Because I think it would be useful to see, it's useful to see the sine graph in relation to the next two graphs we're going to do, okay? So, f of x equals k plus or minus a sine of bx minus h. What are the parts of it again? K is my what?
Vertical shift.
Vertical shift. Tells me what the new sinusoidal axis is. Okay. Next part. A is the amplitude, or specifically the absolute value of A is the amplitude. Okay. Good. Next one. 2 pi over absolute value of B is my period. And last one. Good. The solution to bx minus h equals 0 represents the phase shift, okay? So, solution to bx minus h equals 0 is my phase shift, okay? Okay? And so, if I'm, all these parts are coming together and they tell me the changes I would need to make to my sine wave so I can make those sine wave changes. So, if I drew out the sine wave, it would look something like that here. This would be the point 0, 0. This is the point pi over 2, 1. This is pi, 0. This one down here is 3 pi over 2, 1, or minus 1, excuse me. And it comes back, it repeats at 2 pi at this point here, okay? So that's your, that's the sine graph right there, this classical sine graph. Cosine graph, as we saw, would be taking that and just scooting it over, okay? Now, it turns out the next set of graphs we're going to look at are the cosecant and the secant graphs, okay? Now, what do we know about the relationship between the secant, cosecant and sine?
Inverse.
Yeah, it's just it's not it's reciprocal. This is where it gets troublesome trying to use the word inverse, because there's a separate form of, there's a separate inverse for these things, okay? And it's just because these things aren't numbers, they're operations, okay? That's how they work, and so we can have a flip of the operation, a reciprocal of it, that's different than the inverse of it, because the inverse of an operation is what undoes the operation. And these don't undo each other, they just flip each other, okay? So, if this is my sine graph, okay, and we know that the cosecant is equal to 1 over the sine, what do you think is going to happen to this graph here? It's going to flip, but how's it going to flip? It's not just going to flip upside down, because if it did that, well, if it went the other way, it would still look exactly the same, remember? It's a sine. It's going to do what? I see you making these motions here.
Parabola.
It's going to actually come undone and form parabola-like shapes wherever the sine has one of its humps, basically. Hump's probably not the best word, but whatever. Okay? Other than that, all these parts here will actually remain the same. okay? So, but the graph itself becomes kind of flipped upside down. So, I'm going to actually copy all these, see if I can do this correctly. Should copy it. Okay. So there's my sine graph. Okay. Control V. Should copy that. Yep, there we go. Okay. And now, all the same pieces, but now we're going to look at, okay, f of x equals k plus or minus a cosecant of bx minus h, okay? So, for the cosecant, all these parts are the same, okay? We have vertical shift, okay, amplitude, period, and phase shift, all found the same exact way we find it for the sine, okay? The graph, though, is different, okay? The graph of the cosecant, okay, you still have a sinusoidal axis, okay? Basically a baseline, the thing follows, so this is the sinusoidal axis, okay? The amplitude is still going to tell you where maximums and minimums are, okay? So, here's a line for the maximum, here's a line for minimums, a line for maximums actually, okay? At y equals, in this case, because our amplitude, if I did, excuse me, I should probably write it out. Okay. Give ourselves some room here. Okay. Okay, because our amplitude is still going to be 1 in this case here. Okay. Okay. Now, period is still going to be 2 pi over b, or 2 pi over absolute value b. So for this one, there's no b, so it's just 2 pi. Okay. So I'm going to mark that period out. Here's where 0 is. Okay. Here's where 2 pi is. Okay. Because we already know from the sine graph, this thing's going to have kind of interesting points at half the period and at the quarter marks of the period, so 1/4 period and 3/4 period. I'll go ahead and mark those. So here's my half period, quarter period, 3/4 period, okay? No phase shift in this case. All right, so now we want to come ahead and graph this. Before I just go ahead and just jump in and start drawing this picture though, let's make ourselves a little chart of what the cosecant's actually doing, okay? So we can refer back to the unit circle, you need this, but the cosecant of x for values of x. When I plug in 0, what's the cosecant of x going to equal? It's 1 over 0, right? Which is?
Undefined.
Undefined. So it doesn't exist there. Okay? How about, I'm going to do something a little strange here. I'm going to actually not do pi over 2 pi, 3 pi over 2, 2 pi. I'll do those points. But first I'm going to do pi over 4. Okay? The cosecant of pi over 4, anybody know what that's going to be?
4 over pi.
4 over pi? Nope. Again, look at your unit circle.
Square root of
So remember,
square root of 2 divided by 2.
yeah, so it would be, so at pi over 4,
Square root of 2, no?
okay, the y coordinate is, it's root 2 over 2, root 2 over 2 is the coordinate, it's pi over 4,
So it has to be.
okay? So cosecant's 1 over y, so the cosecant should be 1 over root 2 over 2.
So 2.
So when I clean that up, I get 2 over root 2, okay? Which actually cleans up to be just 2. Not just 2, it's just root 2, excuse me. okay, when you clean it all up, okay? So, this is equal to root 2 there, okay? Or is root 2 bigger or smaller than 1?
Smaller.
It's bigger, okay?
Yeah, one,
Square root
yeah.
of 2, it's gotta be bigger than 1,
Yeah.
okay? Square root of 2 is bigger than 1, in fact it's equal to about 1.414, okay? So if you're graphing, about 1.5 would be good enough, okay? So we're actually above this dotted line here. That's kind of weird. Pi over 2, what am I equal to? And pi over 2, cosecant pi over 2 is?
So, 1 divided by 1.
1 divided by 1, which is? 1.
That's
Okay.
easy.
Okay. At 3 pi over 4, okay, it's going to be, on this side, it's still going to be root 2 over 2, which means it should be equal to root 2, okay?
Oh, right, yeah.
And if I did pi, what's this thing equal to? It's undefined again, right? And at this point here, if I did 3 pi over 2, what do I get? Should be -1. And finally, at 2 pi, it's what again? Undefined. Okay? So, this thing has locations where it's undefined. In fact, wherever the sine graph would return to the sinusoidal axis, the cosecant graph would have an asymptote. Okay? So this thing actually has asymptotes, which I can mark. There's one right there at 0, 0, one right there at pi, one right there at 2 pi, okay? And filling in the other locations here, we did pi over 4 and 3 pi over 4. Those were equal to about, again, 1.5, okay? So there's 1, 2, so 1.5 would be like right there, and put another one right there, and we have a point down there. So the thing comes down and forms a curve just like that, okay? And so if I'm marking these points here, this is pi over 4, root 2, 3 pi over 4, root 2, okay? And then pi over 2, 1, okay? So, it should do the same exact thing down here. In fact, if I did 5 pi over 4 on the graph and 7 pi over 4, they would be equal to minus root 2 respectively, excuse me, okay? And so, graphing this thing out, notice how I get just these two, one cycle of it is just two kind of weird looking parabolas that flipped from up and down, okay? By the way, if I repeat this thing, guess what it's going to do next? Flip back up, have another parabola up there, then flip back down, have another one down there. It's going to keep oscillating like that, back and forth, back and forth. And in fact, if I threw on here, okay, nope, there we go. If I threw on here the sine graph, okay, notice they match up. Okay, so that's the yellow is the sine of x. Okay, it matches up with the humps just like that. Okay, so it goes through and just repeats kind of back and forth exactly that. Okay, all the parts are still the same. So when I'm measuring amplitude for the cosecant, this time my amplitude is measured. It's the same as the amplitude for the sine, except instead of being still from this point right here to the baseline, okay? So it's still my amp, okay? Period is still 2 pi. That's how long it takes for it to repeat, okay? Phase shift is still where it starts, okay? And vertical shift is still where the sinusoidal axis is on this thing, okay? So all the parts are just the same, it's just the graph has been kind of ripped inside out, if you will, Okay? So, that's the cosecant graph. Anyone want to take a guess what the secant graph is going to look like?
Flip it up. Or move it over.
Move it over, because the secant would go with what?
Cosine.
The cosine. Okay? The secant and the cosine go hand in hand, and so if I were to do the same thing for the secant, it would be basically the same sort of graph as the cosine. In fact, the secant graph, if we did it real fast, again, all those parts are going to be the same, but the cosine graph, actually I don't want to do that, let's do it with this. The cosine graph, remember, looked like that right there, okay? So my secant graph, okay, it's going to have asymptotes wherever the cosine reaches 0, so this would be at pi over 2 and 3 pi over 2, okay? And then right here at 0, 0, okay, at pi and at 2 pi is where we meet up. So this one again is cosine of x, and in the yellow, sorry, whoops, got it backwards. The yellow is the cosine of x, okay, and this one is the secant of x. Okay, but notice how the relationship is exactly the same. It's just shifted over from what the sine was. Okay, so you get these parabola things. Okay, these parabola things wherever the cosine has a maximum or a minimum. Okay, all right. Any questions about how secant or cosecant or secant works? Okay. If I were to write one up with a lot of the changes that we would make, okay, we would approach it the exact same way as we would the sine cosine graph. We just note that it's cosecant or secant instead. Okay, so I would still find my amplitude, I'd still find my phase shift, I'd still find my vertical shift, I'd still find my period. All those I would find the same exact way I would for sine or cosine. And then when it comes out to graphing, I just realize I'm inverting, or I'm reciprocating the thing. I'm ripping it inside out, if you will. Okay?
So, should we draw the cosine, or as a help?
As a help, you absolutely can. In fact, a lot of people, when they're first doing this out, will. They'll do a quick sketch of what the cosine or sine graph looks for that, so they can use that to help aid them in the graph of this right here. So like a dotted line cosine or a dotted line sine really can help you kind of get the proper picture of what's going on. Okay? Now, if I were to graph this, by the way, on a calculator, okay, I want to reiterate because a few people still had trouble with this on the test. Okay, on a calculator though, where is by? I'll just use the
left.
Right there. Thank you. Okay. Maybe not. Maybe he's not going to come up today. Come on, wake up.
There you go.
Okay. So, on the calculator, if I wanted to graph one of these things, okay, I have to, the calculator doesn't have a cosecant button, doesn't have a secant button, doesn't have anything like that. So you have to use that reciprocal identity we saw. We have to flip it upside down, okay? So, I'll do the sine of x, and we'll compare it to the cosecant of x, which will enter the calculator as 1 divided by parentheses sine of x, okay? That's how you have to handle cosecant on a calculator, okay? If we graph this out, oh, I know what's going on. Silly me. I'm in degrees. I should be in radians if I want to graph this properly done. Okay.
Amateur move.
Yep.
Hey, what is
Well, I'm doing it in degrees. It's changing the x-axis, and the period goes from being 2 pi to 360. So it makes everything like huge.
that?
Okay.
Makes sense.
That's really the big graphing difference you'll see. There we go. Much better looking. Okay? There's my sine graph, and there's my cosecant graph. And so you can see there are a bunch of parabolas. What I'm going to do here to illustrate how this is going to work, I'm going to zoom in on this location over here. Okay? So I'm going to hit the window button, tell it x minimum, we don't need it to be that big. We'll make it
Negative.
2. Okay, and maximum we'll make 2 as well. The y minimum, we'll just make -1. The y maximum, we're doing it from 0 to 2 pi is the normal period. So 2 pi is about 6.28, so let's make it 7. Okay. And that'll give us a good picture of what I just did. I think I did it backwards. I flipped them. Whoops.
Wait, there's no.
Let's fix this. This is -1.
That's good.
-2, +2. There we go. That's better. Yes.
I get this graph.
Oh.
What on earth is happening? I have no idea. Yes. You can press exit if you want to see how.
Okay. Well, one thing is these things are all, your window, your viewing window is really weird. So let's go ahead and just do the same thing. So x minimum was -1.
Oh, okay.
X maximum we made what, 7?
Yeah.
Okay. Same there. Go back. No.
Okay. It's different.
Y minimum is, what did I say, -2?
Yes.
Y maximum 2.
That's good.
Alright, now let's see.
I'm sorry.
Yeah, hang on one second. Where's the quit?
It's
Okay.
wow. Sorry.
It's alright. It's got a different. There it goes.
Oh.
Now you have a
Perfect.
better
Awesome.
picture.
Thank you.
Okay. And so you can see from there how the calculator works with that. So you can see the 2 graphs together on the calculator. Okay. With all the pieces. There's my sine graph. Okay. And then my cosecant graph comes down, touches there, comes back up, does the same thing, and it repeats. You can see it's starting to repeat on either side there. Okay. And so that's how you get it to be done. Okay. Any questions about how this works with these 2 graphs? Okay, let's look now at the last 2, the tangent and the cotangent. Okay, so tangent and cotangent are different. Okay, they're not going to behave the same way as the sine, cosine, cosecant, secant behave. Excuse me. Okay, so we're going to look at, in this case, f of x equals k plus or minus a tangent of bx minus h. Okay. The first big thing that's different about let's not say first big thing, but let's just go through here and start marking off all the pieces. K is still my vertical shift. Absolute value of A is still my amplitude, okay? But with the tangent graph, as you're going to see here in a second, the amplitude doesn't really do very much, okay? In fact, I don't even necessarily need to put this under with absolute values, because all the amplitude is really going to tell me in this case here is it's going to basically be the same as a regular stretch and flip is for a regular sine or regular graph. Okay, so regular. That's not how you spell regular. Regulate. I've got Warren G stuck in my head. Regular stretch dash flip. Okay. In this case here. So if you remember, when we had a number out front of the thing with x and like the polynomial, it told you how you stretch the graph. It also told you if you flip the graph upside down or not. Okay, this is going to do the same thing as that there. Okay, so it's not the same as it is for sine or cosine, where it's telling you the distance from the sinusoidal axis to the maximum or minimum. Here it's just telling you how the thing is stretched. Okay. I'm going to skip period. We're going to first do phase shift. phase shift is still the solution to bx minus h equals 0. That's still my phase shift. Okay? Okay? But the last one now, the period is different. Okay? The period for the tangent is going to be pi over the absolute value of b, not 2 pi over the absolute value of b. Okay? Why would that be the case? Anybody know? Can think of it? Think of the unit circle. What's happening on the unit circle? Okay? Tangent represents what?
The
Y over x, right? Okay? And if I started down here at negative pi over 2, okay? This here would be negative pi over 3, negative pi over 4, negative pi over 6, 0, pi over 6, pi over 4, pi over 3, pi over 2, okay? The numbers here do what? They're the same throughout, right? The only thing that flips is as I come down, okay, basically, what changes is minus signs. Right here, the minus signs change, becomes positive, and these all become positive, right? Up here. When I hit 2 pi, or pi over 2, on this side, x becomes negative, which means all the values become negative again. And when I hit down here in my third quadrant, they're both negative, which means if I do y over x, they become positive, don't they? A negative divided by negative is a positive number, okay? And so you can think of this as being negative, 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 positive, 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 and then flip, negative, 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 positive, positive, positive. So it goes through, okay? Oh, what are they doing over there? There's something going on over there. It's like I think they're emptying a fire hydrant.
Wait,
You're
what?
looking. Okay.
Okay.
All right. So right there, as you can see, it goes. It'll be negative, negative, negative in this zone. Then positives, then negatives, then positives again. Okay. As it goes around the circle, it just repeats it that way there. So it does a full cycle of positive and negative in a distance of pi instead of a distance of 2 pi. Okay. As it goes around the circle. Okay. So that's why the period is pi over b in this case. Okay. Now let's go ahead and draw out what the tangent graph looks like. If you noticed over there, I started at negative pi over 2 instead of at 0. Okay? There's a reason for that. At negative pi over 2, what's the value of the tangent? It's what? It's negative 1 over 0, right? Which is? Undefined. So I've got asymptotes at negative pi over 2, and again, at pi over 2. I'm going to have the same thing, right? So asymptote right there. Asymptote right there, okay? All right. In this case here, since our period is now from pi over b, I'm still going to approach it kind of doing the same thing I did before, where I'm going to do the halfway point and then the quarter point and the 3/4 point, because that'll help me get my graph going, okay? The halfway point of a period of pi is going to be, or this thing right here is going to be where? 0, right? And when this is 0, what's the tangent equal to? The coordinate there would be 1, 0.
Oh, one.
Not defined, because it's y over x, not x over y.
0, 1.
So it's 0 over 1, which is 0. So it crosses the x-axis at the origin, okay, of this thing here. All right, my next points would be at the negative pi over 4 mark and the pi over 4 mark. What's special about pi over 4 on the unit circle? The x and y values are what there? They're the same. So what's the tangent always going to be?
1.
1. Okay, 1 or negative 1 depending on where we are. So at negative pi over 4, we're actually down here at negative 1. Put that mark there. And at pi over 4, we're at positive 1. So we're right there. Okay? Now, to finish this thing off, because it's not just going to be a straight line between these points, these things curve. Okay? If I were to put like pi over 6's on here, you'd notice they're close to 0, kind of in those locations. I would put pi over 3's, they're going to be up and over there. So this thing actually would kind of come down like so, and kind of come up like that. Okay? And so you get this windmill-ish looking thing in the center. In fact, what does that look suspiciously a lot like? Yeah, the dancing guy, the x cubed graph, doesn't it? Okay? It looks very similar to that, but it's confined because it's got these asymptotes, and because this thing is a tangent graph, guess what it's going to do? It's going to repeat.
Yeah.
So it's going to do the same thing over here, like that, and the same thing on the other side. So it just repeats that picture over and over and over again. So we're going to throw up a tangent now on my graph here. Oh no. There it goes. X. Where's my X? Okay. And again, I want to change my window. My X minimum, 2 works for it. My X maximum, positive 2 works. Y minimum, actually those are fine for the Y's. Okay? And as you'll see here, okay, the tangent graph. Oh, there's the calculator when I reset it, went back to degrees. Shoot. Needs to stop doing that. There we go. There we go. Okay. Now remember, this is really zoomed up, but you can see the picture we get. Okay, it does this windmill-ish thing in there, and then it's got it repeats itself. Okay, so there's an asymptote right here, pi over 2 at negative pi over 2. Okay, but it's going to repeat that picture there. Okay, that's the graph of the tangent. Okay, and again, all these things are going to work the same way to shift the graph around. So if I change the vertical shift, I move the sinusoidal axis up and down, which will change where the tangent, basically how the tangent crosses. Okay. If I change the phase shift, I move this thing left to right. Okay. Amplitude in this case, as you notice, there's no maximum, no minimum. Okay. That's why the amplitude doesn't work the same way. But what it can do is it can stretch this thing out in this direction or compress it down in this direction. Okay. Or if I made it negative, it would flip it. So it would flip it from being like this, it'd flip it 180 degrees. Okay. So on and so forth. So all the parts are still there. They just work a bit differently because this is a tangent, not a sine. Okay. If I went through with the cotangent graph. Okay. It's going to have all the same pieces as the tangent graph did. Okay. So it still has vertical shift. The amplitude works the same way as that tangent graph does. Okay. So the amplitude again is just going to be A. I'm going to write same as tangent. Okay. Period is going to still be pi over the absolute value of B. Okay. Vertical shift and phase shift still work the same way. Okay. The difference with the cotangent though is instead of going from negative pi over 2 to pi over 2, it's going to start at 0 and end at pi. Okay? Because again, it's kind of shifted over just the same way the cosine is shifted over. Okay? The other big thing it does is look at that. If it starts at 0, it starts off being what? Positive or negative? Positive, right? And then it becomes negative. So it flips
Oh yeah, actually.
It reciprocates the tangent graph the same way that the cosecant reciprocated the sine graph. Okay? So it flips it around. So if we were to draw this thing out fully, okay, here's where 0 is, here's where pi is, here's pi over 2, and I'll do the same thing as before. Mark pi over 4 and 3 pi over 4 out on this graph. Okay? There's asymptotes at 0 and pi. Again, if you need to confirm that, just look at your unit circle, get those values there. Okay? It returns to 0 at pi over 2. At pi over 4, it's equal to 1. At 3 pi over 4, it's equal to negative 1. And if I fill in the... let's do this better. I'm not doing good graph. And so it comes down just like that. And it repeats. Okay? So, just like before, it's going to repeat. And so there's what your cotangent graph is going to look like. Okay? Exactly like the tangent graph. Okay? But pushed over by pi over 2. Okay? And flipped. And so if I added it to the calculator graph, okay? We did the cotangent here. So it'd be 1 divided by the tangent, just like we did with the other one. Okay? I'm going to go ahead and readjust this window so we can see it better. So my x maximum, let's make it 4 now. Okay. You'll see the tangent graph first. So this is the tangent graph going first. And now you'll see the cotangent come second. And you notice it's just the flip of what the tangent was doing. Okay? So you get these two kind of lattice looking things. Okay? Alright, good. Any questions about how any of this graphing works? Okay? Alright, tomorrow we'll spend some time looking at it more and doing kind of the actual shifts and changes.
The intersection where they cross each other, is that of any importance to us?
Not really, but where they cross each other is at, the location would be where x, y is 1.
Oh, right,
Because that's where they both have y equals 1.
Oh, that's...
Okay.
Yeah,
So,
that's really
pi, it's basically telling you pi over 4, 3 pi over 4, negative pi, etc. Okay?
Yes.
Alright everybody, have a good afternoon.
You too, sir.
I'll see you mañana.